continue with this idea from section 2.1, which was Monday's class. And recall that the domain was the set. It's a set of all inputs, and the range is a set of all outputs. So anytime you talk about a domain or a range, you've got to be using some type of notation that defines a set. So for us, the easiest way to do it, a set that's infinite, is to use interval notation. So in this graph, visually, if this is your entire function f, I know the name of this function is f because I see that letter right there, f of x. So the function is f. I've graphed the function f. And where does this function begin? It begins right here and it ends right there. So if those two points were called x1 and x2, my domain is everything including x1 up to x2. So my domain would be written like this. It's the set of all x values that are legal, legitimate inputs into your function. Similarly, your range is all the outputs. So you look for your smallest output value and your largest output value, and you just say, okay, everything in between there is an output of this function f. So this would be your, right here would be your domain, the interval that defines your domain, and your range would be everything from the corresponding y1 up to the corresponding y2, including those values. Okay. So that image of thinking about these intervals on each axis is a way of thinking about your range when you have your picture. And another way of doing that is this little thing I was just trying to find forever and ever right here. And so here we have a function, and our function, and it's just an artifact of this particular drawing. All these circles are really solid circles right here. So if I asked you what the domain is of this particular function, notice the domain has to be talked about in two separate pieces, because you've got the function that goes from point A to point C, and then you've got the curve here from E to C2. Okay, so when we talk about the domain here, we have to have two sets, and we have to put a union in between them, because it's going to be the union of those two sets. So here's a beautiful animation to visually give you a sense of the domain. I think that is so cool when I first saw that. Woo-hoo. Okay, so there's your domain. So your domain starts here at value 2. It goes up to 6. And then it stops. So that's my first interval, 2 to 6. I'm going to now union that interval. Notice my union doesn't have a little stem on it. It's like a U without the stem. A lot of you put U on it. And then the rest of my interval goes from 7 to 15. So I put 7, 15. So that's my domain for that function. Okay. So let's see what the range looks like. Okay, so there's the range. The range starts, the low point of the range is at -2. And the range goes from -2 to just a little bit past 2. Let's call that what, 2 1/4 or something? We'll guesstimate. Then it stops. There's nothing between 2 1/4 and 4. So we union that with 4 to 6. So that's our range. Any questions on domain and range and how you would, from looking at a graph anyway, how you would actually express the intervals for the domain and the range? Anything? Okay, so let's go back to our notes. Okay, so what I'd like you to do, let's do this first picture here together. Find the domain and range of the function illustrated below. Okay. To find the domain, look along the x-axis to find the inputs that correspond to the points on the graph. Use interval notation to represent the domain. So let's look along our x-axis does this graph actually have a beginning point? A smallest value where you're beginning? Yep. What is it? -7, right, Brittany? Okay, so I'm going to start right here at -7, and I'm going to put my staple right on there. And as I move to the right, I see that my graph has corresponding points, and I'm going to keep going. And where do I stop? I never stop because the right-hand side of this graph has an arrow. My x-axis goes all the way out to infinity, which is not a specific value, so I use my parenthesis. So what I'd like you to do at your seats with your table, Ben, do you mind joining Brittany so you two could just discuss your answers today? Oh, I don't want you to be loners. Okay. So at your seats, see if you and your table mates can define what the range is here. Right. So the range of this function, does it have an absolute low point? Yes. And the y value, because the range is all your output. So the smallest output starts right here at -2. And the function is defined. Where do I stop? Never, because of that arrow right there. So my range is going to start at -2, and it never stops, positive infinity. Okay. Any questions on that? I'm glad I have someone taking care of me. Thank you. All right. All right. So what I'd like, we have, well, we almost have 3 tables. We've got 3.5 tables. So I'd like table number 1 to do to identify domain and range of this first graph. And I'd like this middle table and that table to do the middle one, and then a representative confer. And then this table do this last one. So everybody's flags are down, and when you're done, everybody on your table, put your flag up.
Bracket -5, 3, bracket 0,
Right, and anytime you guys are done early today, because I know you probably didn't take my advice, because nobody ever does.
I wasn't here Monday.
All right, no. Be working on this. Just go back to pages 6 and 7. You may want to separate it, you may not, or just keep it open. I don't know, check with your group. Check with them. You all agree?
Yeah.
Okay, flag up. Okay, so okay, well, pretty quickly. So let's take a look here. So table number 2, you were responsible for the domain and range of this graph here. So what did you get for your domain, Cooper? Yep. And the range, CJ? Okay, good. And tables 3 and 5 had responsibility for the domain and range. Brittany, how about the domain on this one? Yeah. Okay, and range, Cambry? Very good. You guys are moving right along here. And table 4, you had domain. So domain, Gina? Well, remember, we're working along the X. And are we moving to the right or left? Right, so positive infinity. Good. Yeah. Yeah, and William, the range?
Bracket 0,
What kind of negative infinity? Yeah.
There's only one K.
You know, there's positive in which direction? So we're starting here with we start here with our range, right? And we're going, look at your direction, and that will help you with the sign of the infinity. Okay, any questions on that from anybody? All right, moving along, singing a song. All right, now what are we going to come up with? This is continuing with the work we did on Monday, just identifying the values, functional values, given a graph versus an equation or a table. So the graph of the function f, so this represents the graph of the function f, and we want to find f of 0. So this is how we read it. F of 0 is how we read it. So our input, our independent variable is 0. So f of 0 corresponds, this notation corresponds to the, what we typically call the y value when x is 0. So that's also called what on our graph, that point, f of 0? Jonah? The other one, right. So when x is 0, f of 0 is 3. So that's the value of your y value of your y-intercept, okay? So 0, 3, another way to write that is 0, comma, f of 0. I just want you to start getting used to this notation. 0, comma, f of 0. F of 0 represents exactly the same thing as this y value of 3. In general, you would write the coordinates for anything on this graph like this, x, comma, and you don't write y anymore, you say f of x. Okay? That's how you write the coordinates for any point on that graph. Now the second question's a little bit different. So this is how this is actually asking us to find the y-intercept, the value for the y-intercept. And this one is asking us to find the values of x that make our function output value y. And what are those usually called? Excuse me, our output function 0. And what are those usually called on our graph? X-intercepts. And remember when we were doing section 1.1 a long time ago, ages ago now, with all the snow days, and we were trying to find the solutions to some really funky algebraic equations. We could set the equation equal to 0, and we went up here on our calculator, and I said, you'll be seeing this again as soon as we do functions, but probably no one ever recalls that. Here it is, second calculate. That's how we found our x-intercept, so where our equations were equal to 0, okay? The reason they put 0 here is everything from like intermediate algebra on uses functional notation. And with functional notation, the x-intercept is where your output of your function is 0, and that's why they call it 0. You're actually finding the x value that makes your equation equal to 0. Okay? So for what x values does the output of this function equal 0? What x values? Can you find them? Negative what? -3 and x equals 2. Right, they're right here. There are the x values that make your output 0. So that's the x values, the x coordinate of your x-intercepts. So this is just fancy ways with functional notation to say, find the value of your y-intercept and find the value of values here of your x-intercepts. And your x-intercepts are now called zeros of your function. That's your new language for many of you. I'm no longer going to say find your x-intercept. I'm going to say find the 0 of this function. And you need to know that it corresponds to this notation. Okay, so as you can see from this graph, you can have multiple x-intercepts. It varies how many x-intercepts you have if you're a function, because you can have lots of different x values along here that go to the, so let's look at this for a minute. You could have multiple x values that go all to the same output called 0. So if you're a function, you can have multiple from 0 to many, many, many x-intercepts. But how many y-intercepts can you have? Remember, here's your y-intercept, you're out here, here's your value 0. How many points here can go to that 0? Did I say that right? Sorry, I got it backwards. I just did the same thing. Here, sorry. your y-intercept, you have 0 right here in your domain. How many places can that go to be a function? One and only one. You can only have one y-intercept because look at where your y-intercept falls. It's on a vertical line, right? And we know that to define a function, you can use the vertical line test, and it can only go through one point. So you can only have one y-intercept. Okay. If you have a function, if you had a relation, then it doesn't matter. Like a circle, right? You could have two y-intercepts for the circle, but that's not a function. It's a relation. That's what we defined on Monday. Okay. So increasing and decreasing and constant functions. I think that sometimes people can get all like bogged down in notation with this, but the idea behind what interval is your function increasing over or what interval is your function decreasing over, my language over, always implies x values, the set of the interval defined over your x values or whatever your independent variable is. It could be time, right? It could be number of units you're supplying for a particular manufacturer. It could be anything, but it's over your independent variable. And this is taken right out of your book. And if you want to refer back to it, these are the pages in your textbook, 229 to 230. And it's a little story in your book that the author was trying to be cute, talking about someone being sick with the flu and having a fever. And they started feeling better over time. And so they started drawing graphs recording their fever. And then I guess they worked too hard, so their fever started to go up, and then it stayed there for a while. So that's the story, the time temperature story. I think it helps us to like look at this idea and make sense, and it's very intuitive. So what's the person's temperature starting at here? 101, right? The initial temperature is always when your time is 0. In this case, our time equals 0 corresponds to what time? What time is time equals 0 to here? 8 a.m., right? So at t equals 0, that corresponds to 8 a.m. So t equals 0, my temperature is 101. Okay? And as time goes along, my temperature is decreasing. Right? So as I move to the right, my output values, or what we typically call our y values, are decreasing. Right? So the interval where my temperature is decreasing is the time over which it's decreasing, the x value. So from 0 to 3, from 0 to 3. Now here's the key for our particular text. Our text and the text that I used prior to this had a different story. They didn't do it this way, but for our text, when they define intervals where your function's increasing, decreasing, or constant, it's always going to be an open interval. That's the key. That's where you want to put your little star here or underline in your notes. It's always going to be an open interval. So you'll always use parentheses. Okay? So over that interval from x equals 0, not including the 0, to x equals 3, not including the 3, my temperature is falling as my time increases. Okay? Again, I think it's intuitive. What open interval is your temperature increasing? Someone help me with that. What open interval is your temperature increasing? 3, 5. What else do I need? Parentheses, right? Okay. And finally, over what open interval is my temperature staying the same, not changing at all? Austin, can you help me with that?
It's not changing.
Yeah. Okay. All right. So again, and you have to just sort of like, some people say, but those look like coordinates, and I agree, and that's always the problem with open intervals. They do look like it looks like a point, but you just have to like look at the context of the question that's being asked. If they're asking for an interval, then you know it's an interval and not a particular point on a graph. Okay. So that's the only confusion sometimes, and it's always over your x values or your independent variable. Okay, so if you were looking at this entire graph right here, this final graph, at what time is your temperature at its lowest? 11 o'clock. 11 o'clock or at x equals 3, which represents 11 a.m., right? Okay. And no problem with that. That's pretty intuitive too. So what did you look for here, Amy? But you picked it up. You picked 11 up right away. What did you look for when I asked you for your? The lowest point on the graph occurs right here at the bottom of that U, and that's called a relative minimum. This is called this point 0, 3 comma. What do we think that is? 98.6, maybe back to normal. Let me write that a little bit clearer so we can see that 3. Okay. This is called our relative minimum. Okay, the relative minimum is 98.6. The relative minimum is 98.6. If I'm interested in the person's lowest temperature, I don't care when it occurred. The relative minimum of this graph is only asking for where is my lowest temperature on that graph from 0 to 7, and my lowest temperature is 98.6 degrees Fahrenheit. Later, you could say it happened to occur at 11 o'clock in the morning. But whenever you're asked for a relative minimum or a relative maximum value, you state the output of your function, what we typically call the y value only. You don't give me the coordinates of the point, you just give me the y value, the output of the function. Okay? That tends to be the mistake that people make often when they're referring to relative maxes and mins. Okay, so this gives you a formal definition of when functions are increasing and decreasing. This is in your book, so take a look at that or review it in your notes. But what I'd like you to do right now is I want you to ignore the picture in your notes. I'm just going to move it over for a minute because I've got another picture. This is from the very first problem in your notes. This is the same graph that we worked on initially in your notes. Let's do this together, and then I'm going to ask you to go ahead and do what's at your seat. So I'm going to change this, and I'm going to change this, and I'm going to change this. So ignore this picture for a minute, that way over here. So here's our graph of f. Here's the graph of f. Okay. What would be the domain? We'll go right around the room. Seth, what's the domain of f? Yeah. Yep. Yep. Parentheses. Good. So our domain here starts at -7 and it goes forever and ever and ever. We already did this, right? And what's the range of f? CJ? -2 to infinity. Okay, so we've covered those earlier. And the zeros we've covered, x equals -3 and x equals 5. Maybe it's a little different, I don't know. Okay, what's f of 0? Brittany, what's f of 0? You can estimate it. Oh, no, I was answering something else. Okay, so you can just estimate where you think the f of 0 is. It's okay. Yeah, looks good to me, 2.5. So what did you say, Gina? Yeah. Look, 1, 2, 3. So how many zeros do I have of this function? 3. So I have x equals -3, x equals -1, and x equals 5. Okay, good. All right, let's go back here now. Boom. All right. Intervals on which f is increasing. So let me help you with this. Intervals where f is increasing. So find your high point. If they're on any portion of your domain, find your high point. So here's my high point. Anything that comes before that, any part of my graph that comes before that high point has to be increasing. So what's the interval where that's increasing? Yep. Oh, you're right. Geez, I'm really like messing up here, huh? There's the point right there. There's your other zero. I'm so sorry. Right there. So how would I wouldn't call that 5, -5. I'd call it maybe -4.9. Right. Thank you. Yep. All right. Okay. Rewind this tape. Okay. So what's the interval where my function, one of the intervals over which my function is increasing? Open interval over which my function is increasing. Cooper, I didn't get a chance to hear from you yet. -3, your x value from -3 to 2 is where my function is increasing. Okay. Yes, yes, absolutely. It's open, so here we go. Now, do I see my function increasing anywhere else? From here, it's my function, so I start with that x value at 5, and I go forever and ever and ever. So union that with 5, comma, infinity. So notice it doesn't tell you here, but it's open intervals. Okay? All right. Open intervals over which my function is decreasing. Can you help me with that, Jonah? One interval where your function is decreasing? Excuse me? 3. Let's see. Let me take everything out here so I can see what's going on. So where is my function decreasing? This one. So where is it decreasing? Yeah. -7 to what kind of 3? Right. So -7 to -3 is one of the open intervals. And could someone else, Ben, tell me another interval where it's decreasing? Yep, you come straight down here.
Yes.
2 to where? 5, right. You're looking at the x values, okay? So we have the open interval, 2 to 5. Okay, 2 to 5. All right. Can someone, now I think we're on table 4. What values of x for which f of x is less than or equal to 0? What does that mean, f of x is less than or equal to 0 anyway? Just visually, where does that occur? Yeah, it's where your graph actually sits below or on the x-axis, right? So where is your graph below the x-axis or on the x-axis? Well, from this interval, -3 to what? -1.25, right? It's below or equal to 0. Okay. What was it? Negative, what did I say? -4.9 to, oops, open. Oh, no. I meant, first of all, let's do it where it's equal to 0. It's equal to 0 at 5, right? But it's supposed to be less than or equal to 0. So do we include this? What do we do here? Union it, right. So there's only one value here, right? 5. You'd union that with -1.1. All agree with this so far? All right. And then there's my set. And then my last set would be from -4.9 to -1.1. So actually, I don't have to do that. I can just say from -4.9 to negative 1.1. And I include those values. I'm not looking at increasing or decreasing anymore. So you always got to keep in mind, oh, when do I use the brackets and when do I use the parentheses? Intervals where you're increasing, decreasing, or constant, always parentheses. Any other question, you have to say, am I including the point or am I not including the point? And that's unioned with the 0.5, right? You can just do that if you want. All right. Now, relative maxima. Relative maxima is the high point. Why do I have an A here? Well, I could have more than one high point. So that's why we use the A. Relative maxima, what is it, if any, and then where do they occur? So is there a relative maximum or maxima here on this graph? Is there a high point? Right here. Relative. It's not absolute. It's anywhere in the neighborhood. So in this neighborhood, if I put a box in there and zoomed in, what's the relative maxima of that box, or the relative maximum of that neighborhood? No. Hang on. I'm going to get there. I'm looking at this neighborhood. If I blew it up, why did I say no to Brittany's 2,5? Right. The maximum is just which part of that point? The y value. So try it again, Brittany. What's the relative maximum here? 5. There we go. The relative maxima is 5. And where does it happen to occur? At what x value? 2. There we go. All right. Good. Yep. Okay. Why is this not the relative maximum? Also, let's go back to where we defined it. Yep. Yeah. Okay. So in order for you to be a relative maximum, you have to be the point. This was on your paper, I thought. I can't find it. Oh, here it is. Okay. I guess I skipped this. I'm sorry, I missed it. Okay. In order for you to be a relative maximum, right here. So this is the point C comma F of C. I'm sorry I missed this one. I usually have like each number on a separate page, and I didn't realize I had it below this. So the relative maximum occurs at x equals C in the relative maximum value. We're always looking for the relative maximum value, is the output value F of C. Now here's why the point -7.6 is not included in that answer. When a function changes from increasing, look, increasing to decreasing, a relative maximum will occur. When a function changes from decreasing to increasing, a relative minimum will occur. So let's look at this point right here. And why am I not saying 6 for those people who thought it was either Cooper or Bin? Why am I not saying that 6 is a relative maximum? Right, because there's nothing happening to the left of -7. I have to be going from, I have no idea, folks. I may have truncated this function. This function could be just coming down like this. Look, I don't know. Because I don't know anything about what's happening to the function before -7, it's not even defined. I can't say that this value here, 6, is a relative maximum because I have no idea. Okay, so in order to define a maximum or a minimum, you have to go for a relative maximum. Your function has to be increasing until it gets to that point and decreasing after. Okay, and we can't use -7.6. Okay, so what about our relative minima? Do we have relative minima here? We've got one that is -2 and one that is 0. We have 2 relative minima. So the relative minima are -2 and 0. And where do they occur? At x equals what? -3 and 5. And they occur at x equals -3 and x equals 5. Okay, so I'm going to set you free now. I'm not going to finish. I'm just going to let you take 10 minutes or so to go back and actually fill out your you try this at your seats. This is sort of like your group activity for today, even though we're not done, but throw in the group activity anytime we want. So you finish off the questions you have for this particular graph. Let's take a look at this. And we'll go through this, I hope, relatively quickly because it looks like everybody's been kind of finished with this mostly for a little bit. So, okay, the domain of this function, anybody? Negative infinity to infinity, or you could simply write whenever that's your answer, all real numbers, like that, all real numbers if you want. That's what that fancy stem R means, all real numbers. All right. The range, how about the range? And this one's a little tricky. What's the range? Almost.
I fixed it like 3 times.
The negative infinity comma 4 I agree with. Can we put a bracket around negative infinity? No, because it, all right. And then what about 4? Brace, bracket, not brace. Yeah. Staple, let's include that number. Zeros of f. The zeros of f are always written as x equals. So what are our zeros of this function? X equals -4 and x equals 4, or you could say x equals plus or minus 4, okay? X equals, I don't want the coordinates for once in my life. F of 0, this corresponds to a single value because this is the y value of your y-intercept. So f of 0 equals 1. Okay, I'm going to move my picture along with me as we go along down here so we know what the heck we're looking at. Here we go. And let's make it a little smaller. All right, so here we go. All right, intervals. Now it says intervals, but we know we really want open intervals, and they're always over the x values. So whatever you have to do to remind yourself of those two features about intervals. Open intervals over the x values where f is decreasing. So go to your high points and look at what happens after that. The values of x open from -2 to 0, because that's where your little relative minimum is going to be at 0, 1. So your values where your, oops, I'm doing decreasing first. I've skipped E. Decreasing is from -2 comma to 0, open. And do I have any other decreasing? Well, we do have another high point, so anything that comes after 3 all the way out to infinity. And that's another place where you can make a mistake. You might be looking at the y outputs and call it negative infinity, but it's always over your x values. Then you put your u in between. Okay, increasing. Here's my high point, so I'm going to be increasing anytime before I get there from negative infinity to -2, union with 0 to 3. Okay, all open. The values of x for which f of x, your picture, your graph is all above the x-axis or sitting right on the x-axis. So you literally just remove all of this part right here. And there you go, from -4 to 4, including -4 and 4 because of that equal sign right there. If it had said, when is f of x greater than 0, you would have parentheses around the -4 and 4. Where's our relative maxima? What are they? My relative maxima is 4 and 2. And where do they occur? At x equals -2 and x equals 3. Did you say something, Gina?
Yeah, I just got a little confused in class.
This one right here?
Yeah, we were looking below the.
Oh, you were looking below. Okay. Okay. You all set now? And relative minima, we only have one relative maximum here. It's 1. That's our smallest value in that neighborhood right there. And it occurs at x equals 0. The value of x for which f of x is 3. Okay, f of x is my output. So I go up to my y axis where I see 3, and I draw a horizontal line straight through y equals 3. This is the horizontal line, and that's the equation for any horizontal line, y equals a constant. And I notice I have 2 spots where f of x is 3, and they occur at -3 and at -1. So when you're solving this for x, you put x equals -3 and x equals -1. F of 5, is the value for f of 5 positive or negative? Well, f of 5 is my x value, and I come down and I touch my curve. I'm below the x-axis, so I am negative. Remember, that's your input. That's your x value. Okay, so we've got one last topic to cover, and that has to do with symmetry. And for symmetry, let me see if I can get this, if I have this ready for us. Okay, symmetry of functions. Okay, and I'm going to try to make this as large as I can, which is, this is as large as I can get it. Here's my function. My function here is f of x equals x to the 4th minus 10x squared plus 9. It's a 4th degree. It is a polynomial function, and this is its picture. And this extends forever and ever in that direction. Okay. So when we talk about a function being even, the definition of an even function is that if you look at the value of the function for x and its opposite, then the value of the function is exactly the same. So let's take a look at one of those. So on in your table, we have what value for x? 2.5, right? And -2.5. So let me try to get, oops, let me show the coordinates here so I can see where I'm going. Oh, I happen to stop right there. Isn't that amazing? Okay, so right here, this little box is the definition of an even function. The value of my outputs, my y values, are the same if I evaluate my function at x and at its opposite. And what that looks like as a picture is, if I took this graph and I folded it right along the y-axis, points that are equidistant from 0, those are called opposites, right? If you're equidistant from zeros, they would mirror each other and be at exactly the same point, in this case below the x-axis. So what that would look like is f of -2.5 is equal to f of 2.5, because both of these values are -14.44. They both have exactly the same output value, even though they're on opposite sides of the y-axis. That's what it would be like. Now, I can go ahead and I was going to have you fill in this table, but you can see that this doesn't change no matter how x changes. As x moves out, I can stop at any point. Here's x, 1.28. Here's its opposite. My y values are the same. Now, you can't show that a function is even by just putting in one specific point. Unfortunately, it doesn't work that way. You have to show that this function is even for all points, all x values. And to do that, if this is your function, so on a quiz or a test, if I say, show whether this function is even, odd, or neither, you'd say, okay, well, let me think about this. Anytime you, well, I don't want to give it away. So first of all, you say, okay, even functions, that's where I fold it around the y-axis. And if my x values are opposite, my f of x and f of -x are exactly the same. So to show that that this is an even function, which we know it is from the picture, you have to show that f of -x is equal to f of x. Well, we already know what f of x equals, so we can fill in one side of this equation right now. Here's f of x right there. X to the 4th minus 10x squared plus 9. So you have to show it algebraically for all x, right? Now you plug into that function the opposite of x. So where I see x, I'm going to put in the opposite of x, and I'm going to raise it to the 4th power. minus 10 times the opposite of x, and I square it, and then I put a 9. And if this left-hand side equals the right-hand side, I get a big smiley face, and I can say, now I've shown that this function is even for all x's, not just a particular x I plug in. So I have to figure out, how do I do this? Remember, this means this. That little dash means -1. And if I take -1 to any even power, what do I get as a result? 1. -1 to the 4th times x to the 4th gives me x to the 4th. So this becomes x to the 4th. What does -1 times x, the whole quantity squared, become? -1 times -1 squared, -1 times -1, 1 and x squared. So this becomes 10x squared plus 9. Lo and behold, I have now shown that this function is even because f of -x is exactly the same as f of x. Thus it is proved. Okay? So that's how you show that a function is even. And this is the most important idea right here about even functions. And that's the visual for why functions are even. Let's move along and do odd functions now. So let's take a look at this function. Okay, and I kind of took up all my space. Odd functions. I wonder if where's my camera? I'll grab my camera. Where's my camera? I think I can get it. I think my camera will, now let's call up, where was I? Which one of these? Here. I'll just take this picture. All right, let's change the function. I just had to call it up. And I don't need my camera. Okay, so this is what we call an odd function. Here's an example of an odd function. Is that the one you have below it? No? All right, then I'll work with what you have at your, I was going to try to show you. Let me just show you what the symmetry here. Well, this isn't, this, I picked the wrong odd function. Let's see, let's try that one. Okay, so here, let's look at what happens as x to the y values when x and -x move along here. Let's show the coordinates. So let's just, I'll just stop it right there. There's x and there's -x. What can you say about their output values? They're opposite, right? They're not the same anymore. And notice as I move along this curve, as x and -x, there we go. Here's 2.91 is -2.91. 11.72, it's opposite. So now for odd functions, this is the idea. If I put x into the function and then I put -x into the function, what are the results? F of -x, which from this picture, here's f of -x, -11.72. It doesn't equal 11.72, which is f of x. It equals the opposite of f of x. So to show odd functions, so let's take a look at this. Write this down. F of x equals x to the 5th minus 10x cubed plus 17x. So if I asked you on a quiz or on your homework to show that, is this even, odd, or neither symmetry, you'd say, okay, if it's even, then this would have to be true. And the minute you see an odd exponent here, and you put -x in there, you know you're not going to get x to the 5th back. You're going to get -x to the 5th. So you don't even have to test that because you see that odd. Okay, so now test for, there's no way it's going to be even. So test for odd symmetry. All right, what does odd symmetry say? If I take opposite values and then I look at their output values, they're not equal, they're opposite of each other. So now let's put in -x. Well, we know f of x is x to the 5th minus 10x cubed plus 17x. So to do this side of the equation, I have to do the opposite of this. So what's the opposite of this? -x to the 5th plus 10x to the 3rd minus 17x. So there's the opposite of f of x. I just changed all of my signs to their opposite. Now I have to see if f of negative x equals that, and then my left side will equal my right side. So I go back to my function and I input negative x to the fifth, whoops, minus 10 times negative x to the third, plus 17 times negative x. And let's see what that equals. Okay, when I have the fifth power here, negative 1 to the fifth is going to give me a negative 1x to the fifth, minus 10. Negative 1 cubed is going to give me a negative 1x cubed. Okay, and that negative 1 is just represented right there. So what do I get here? I get negative x to the fifth plus 10x cubed minus 17x. Voila. That's the opposite of my original function. This is odd. Sometimes you have to check them out, both of them out, and you won't get an odd or an even function. It's just neither. Okay? So that's the story, Morning Glories, and I'll see you on Friday.